Today we're going to cover some mathematics and how we use it for our problem solving. So let's start with the basics. Computer science is just a subset of mathematics. So we will often require some mathematical analysis to solve a problem efficiently. And sometimes even we can simplify our code just by using a bit of math. We can, for example, unwind some for loops, make them constant operations, so we can speed up our code. Some problems have solutions which just form a pattern. And if we find this pattern, then we can solve the problem. So this is what we would classify as a mathematical ad hoc problem. And all you need to solve the problem is the mathematical intuition. So some tricks you want to keep in mind are you should solve small instances of the problem by hand. And then see if these solutions form some pattern which you can perhaps find a closed formula to. Sometimes this pattern involves an overlapping subproblem. And then we might need to use dynamic programming. It's also quite useful to know some identities and some common sequences, such as the Fibonacci sequence. So a common pattern is something like this: 2, and then 5, 8, 11, 14. It increases by 3 each time. And this is what's known as an arithmetic progression. So the recurrence is just based on the last element, and then you add some constant to it. Now if you have an arithmetic progression, you may want to get the nth element. You can do that by first finding this constant c, and then you multiply it by n minus 1 and add the first element of the sequence. If you want the sum of the arithmetic progression, then you calculate an expression which might seem a bit familiar. It's n times the sum of the first and the nth element over 2. And for example, if you look at the sum of the integers from 1 up to n, so this is an arithmetic progression where the constant is 1 and a1 is also 1. So then we get n times n plus 1 divided by 2. We also have geometric progressions. So here the value multiplies by 2 each time. Generally, you have some original value s, and then you have the value being multiplied with it at each step, r. So first the sequence starts with s, and then you have s times r, and s times r squared, s times r cubed, and so on. If you want to sum over a finite portion of this, then you can calculate this expression. So it's 1 minus r to the power of n times s over 1 minus r. And if you want to calculate the sum from the mth element to the nth element, so you're doing a range of the sequence, then you need to change the expression just a little bit. There are cases where using logarithm is much better than working with the numbers directly. Most programming languages, at least all the ones I can think of, have some built-in natural logarithm function. And then you might have base 10 logarithm, and also a function for the exponential. So that's e to the power of x. So one of these problems is, for example, what's the first power of 17 that has k digits in base b? The naive solution is just to iterate over the powers of 17 and then count the number of digits. So it starts at 1, it has 1 digit, then we multiply it by 17, count the number of digits there, until we reach k. But of course we're raising 17 to some power, so this grows exponentially. And 17 to the power of 16 is greater than 2 to the power of 64. So what if k is a large number, such as 500? Very quickly, these numbers are going to be too big to work with, even if you have a big integer class. They're just going to be too large for memory, the operations are going to become slow. So why don't we use the logarithm? You can calculate the length of a number in base b by taking the logarithm of the number in that base, flooring it, and then adding 1. But how do you do this if we only have access to the natural logarithm, or we only have access to base 10 logarithm? We change base. So if we want the logarithm of a in base b, but we only have access to logarithm in base d, or the natural logarithm, then you just take the ratio of the natural logarithm of the number we're working with divided by the natural logarithm of the base you want. And now you can count the length without converting bases. We still have to iterate over the powers of 17, but we can do that using the logarithm. So if you want to find the logarithm of 17 to the power of x, so that's this here, we have 17 to the power of x minus 1 times 17. That would be 17 to the power of x. This is just equal to the logarithm of 17 to the power of x minus 1 plus the logarithm of 17. So multiplication within the log function is like adding two different logarithm functions, or logarithm calls. And more generally, you have the base here, log in base b of x times y. That's just equal to log base b of x plus log base b of y. And similarly for division, you just subtract instead of adding. And we can simplify this even more. The solution to our problem is simply finding the x for log base b of 17 to the power of x is equal to k minus 1. So one more handy identity we can use is the log base b of a to the power of c is equal to c times log log to the base b of a. So this is just using an iterated version of this rule. And using this identity and what we covered before, we can find that the answer for x is the ceiling of k minus 1 times the natural log of 10 divided by the natural log of 17. Since we're on the topic of bases, let's look at another thing. What if we actually need to convert bases with numbers? So there's a simple algorithm for that. We take as input a base and a value, and while the value is non-zero, we push back the remainder of the value modulo the base, and then we perform integer division on the base. So here we're essentially calculating the multiple of each power of the base. So how many 1s do we have? How many b's do we have? How many b squared? And you can consider what happens when the base is 10, for example. Okay, so when you're working with doubles, comparing them directly can be problematic because you have these errors in precision that come from just using arithmetic operations. For example, if you do k times some double number, and then in another place you add this double number with itself k times, you may get different results. So There's always this matter of precision when working with double numbers. So what can we do differently than we do with integers? We simply compare them to a certain degree of precision. So we will consider two numbers to be equal if their difference is less than some number. A common value for this is 10 to the power of -9, and it's often called an epsilon. So we define our epsilon value, and then we take the absolute of a minus b and check is that less than eps. And then they are considered equal. We could have our less than operator, so we say if a is less than b minus eps, then it is definitely less than b. Less than or equal, we have a is less than b plus eps, so then we allow it to be just slightly above b, and we would be considering it equal. And then the rest of the operators are quite similar. You're just flipping the comparison operator. So this allows us to compare numbers with less worries about precision. We can even use a set. So we define our comparator, which compares the numbers and orders them for our binary search tree. And then we can have a set of doubles with the comparator. So next up is number theory. We've seen a couple of these problems so far. They ask you to output the answer modulo n. And what this tells us is that we can do all the computations in the problem, or at least most of them, with the integers modulo n. And the integers modulo n form a structure called a ring. And it has some special rules which apply, and some interesting properties to be aware of. So first up, let's look at the operations we can apply. So if you calculate a plus b mod n, then it will give you the same value as if you calculate a mod n and b mod n, add them together, and then take modulo n again. So addition works without any problems. You can always just modulo a number by n without worrying about when you're doing it. Same with subtraction. Although you need to be aware of how modulo works in your programming language. For example, in C++, it works differently than in Python. Python does it the way I would consider correct. I think C++ does it in the wrong way.
Could you explain that? Because that's new information for me.
So if you're using negative numbers, you might get negative numbers from your modulo. So if you, for example, take -1 modulo 5. So I can actually just show this. Okay, so we have some number n, we say it's -5, and we have our modulo, which is 7. So now we get -5 here. If we use Python, so let's open Python. But okay, it did not open Python. Here we go, Python. I had -5 modulo 7, so we get 2. So when we take the value of n modulo m, we expect the numbers to be between 0 up to m-1. However, C++ gives us a value which is a bit different. It's the remainder, essentially. So it kind of goes in the other direction when doing negative numbers. Because what we have here is we have -5 is equal to 0 times 7 plus -5. But Python essentially says that -5 is equal to 1 times 7. No, -1 times 7 plus 2. So in C++, what you want to do often is just add m to your number and then take the modulo. And then if you're subtracting and you go a bit below 0, adding m will take you back up into the range of 0 to m-1. You can do multiplication as well, and exponentiation. However, you cannot do division. So what can happen is you can end up with a fraction. So if you do, for example, 9 divided by 2, you get 4.5. What you need to do is you need to find what's called the multiplicative inverse. And the multiplicative inverse of an integer a is the element a to the power of -1, such that we get the identity if we multiply a with its inverse. And the identity of multiplication is 1 here, because if you multiply something in 1, it stays the same. Can we do logarithm? Yeah, we actually can, but it's difficult. Logarithm modulo n is the basis for some cryptography, such as elliptic curve, Diffie-Hellman, many others. You can look up the discrete logarithm if you want to find out some more. You can also take a course at Reykjavik University, cryptography and number theory. Some useful functions and ideas. Prime numbers, they are positive integers greater than 1 that have no positive divisors other than 1 and itself. And we have the GCD and the LCM functions. So the greatest common divisor of two integers a and b is the largest number which divides both of them. And the least common multiple of two integers a and b is the smallest integers that both a and b divide. A prime factor of a positive integer is a prime number which divides it. And the prime factorization of an integer is the decomposition of it into its prime factors. And by the fundamental theorem of arithmetics, every integer greater than 1 has a unique prime factorization. And this fact can be very useful. For the greatest common divisor, we have the Euclidean algorithm. It's a recursive algorithm. It's quite short and simple. So if b is equal to 0, then the GCD of a and b is just a. Otherwise, it is the GCD of b and the remainder of a divided by b. And this function is logarithmic in time complexity. And we can use this to calculate the LCM function. So if you multiply a by b, and then you remove the greatest common divisor of a and b, so you're removing what was common in a and b in prime factors, then you get the least common multiple of a and b. If you reverse the steps taken by the Euclidean algorithm, we get what's known as Bezout's identity. This simply states that there always exists an x and a y such that the equation here holds. And if you have the extended Euclidean algorithm, it computes the GCD and also computes the values of x and y. And in each iteration, it adds up how much of b we subtracted from a and how much of a we subtracted from b. So here we have the base case, as last time. Note that these values here are passed as references, so in each function call, when we modify them here, they get modified for the entire call tree. So what are the applications of this? Well, it's used a lot in factorization algorithms, in cryptography, such as the RSA algorithm. It's often used in proofs for number theory, and it has many other applications in algorithms. Now, how do we determine if a number is a prime? We can naively iterate over all the numbers that are greater than 1 but smaller than n, and just check if that number divides n. This would be an O of n method, which is not good if n is getting large. Now, we can improve our idea. If n is not a prime, then its largest, or it must have a divisor which is less than or equal to the square root of n. So if you think about numbers which are squares of primes, like 49, its prime factorization is 7 times 7. Since 49 is not a prime, there must be some prime in its prime factorization which is less than the square root of 49. Because if the first divisor we had was greater, say 8, then 49 divided by 8 is going to be less than 8. So we would have found it before. So what we do is we iterate up to the square root of n instead, and then our time complexity changes to O of square root of n. Now, if n is not a prime, it has a prime divisor less than or equal to the square root of n. So what we can do is iterate over the prime numbers up to the square root of n. Now there are approximately n divided by the natural logarithm of n primes less than n. So our time complexity improves a little bit. Trial division is a very simplistic, but it is deterministic. So it always returns the same values. Many other algorithms which test for primality are probabilistic or randomized in some way. We have Fermat's test, which uses Fermat's little theorem to test for primality. A very popular algorithm to use is the Miller-Rabin algorithm. It's a probabilistic algorithm which can prove that a number is composite. So if you run it on the same number with a different variable multiple times, and you always get that it couldn't prove it was composite, then it's highly likely to be prime. We also have AKS primality test, which proved that primality testing is in P, so poly time. Now if you want to generate all the primes up to some value, then testing each one of them is not very efficient. Instead, we'll use a method called the Sieve of Eratosthenes. So what we do is, for all numbers from 2 to the square root of n, if the number is not marked, we iterate over every multiple of this number up to n and mark them. The numbers which are left unmarked are those that are not a multiple of any smaller number. The time complexity of this is square root of n times the log of n. So let's go over an example of how this works. We're going up to the number 25. So 2 is unmarked. So we mark all of its multiples and then move on to the next number. 3 is unmarked. So we mark all of its multiples and move on to the next number. 4 is marked, so we skip it and we go straight to 5. Now we mark all of the multiples of 5 and then move on to the next number. 6 is marked, so we skip it and go to 7. Mark all the multiples of 7, then 11, 13, 17, 19, 23. So now we have all the prime numbers less than 25. So we have this Boolean array, which tells us if a number is marked. We have our result vector of primes. We start at the value 2, and we iterate until the value we're at to the power of 2 is greater than n. So essentially when we go past the square root of n. If the value is not marked, then it is a prime, so we add it to our result vector, and then we go through all of its multiples and mark it. Then afterwards we have some values which are greater than the square root of n, which may be primes. So we iterate up to n here and add them if they're not marked. Now, the fundamental theorem of arithmetic, states that every integer greater than 1 is unique product of primes. So we can write n as p1 to the power of e1 times p2 to the power of e2, and so on. So we can store integers as lists of their prime powers. And what we do is we use the Sieve of Eratosthenes to generate all the primes up to the square root of n. Then we iterate over all the primes that we generated and check if they divide n. And we determine the largest power that divides n. So here we go through all the primes, and we start with power equal to 0. So that would be this prime to the power of 0, that's just 1. And then while the remainder of n modulo the prime is 0, so while it divides n, we increase the power and then divide by the prime to reduce n. If the power we obtained is non-zero, we add it to our factors map. And then finally, at the end, we may have a prime number for n here. And we say that it just has, since it's prime, this is just to the power of 1. So now we have the integer stored as a map of the prime to its power. So what we can do with this, for example, is we can calculate the number of divisors. So that's the sigma 0 function of n. We can also calculate the sum of all divisors in the xth power. So this is a generalized version. Sigma x.
The sigma 0 function, shouldn't that be ei plus 1?
Yeah, that should be ei plus 1. That's correct. It's just a typo. Yeah, so it's the... Here, if you consider how many ways you can pick out prime factors in the number. You can take 0 up to ei of each exponent. You can kind of pick the prime 0 to ei many times. And then you have ei plus 1 choices for each prime. And if you multiply those together, that's all the options you have. So that's all the numbers that could divide n. And you can see that if you plug in 0 for x here, then you get the same thing here. Another useful function is Euler's totient function. This tells you how many numbers from 1 up to n minus 1 have GCD of x and n equal to 1. So how many are co-prime with it? How many don't share any prime factor with n?
You say x, like, so where does k come from in the totient function?
Oh, sorry. Did I write this down wrong? I'm sorry, I wrote this down a bit differently. Yeah, so it's essentially every prime that divides n. We want to iterate through those, and then it's 1 minus 1 over that prime for each of those. So the k is the number of primes. Sorry, this should just be simpler if it was just for every prime which divides n. for every prime factor of n.
Right. And an implementation, right, is obviously not so easy, right? If we were just to do this, for what we see, I mean, the division would yield stupid answers.
The implementation is not that hard.
No, but it's not as naive as just punching in what we see here.
Yeah. So, I mean, there are different ways of doing it, and usually you want what's fastest. Let's see. Let me find. Euler phi. Yeah, I mean, I guess it's kind of complicated to do fast, but if you just go for a naive version, it shouldn't be that difficult. You just need to, collect the prime factors of n. And I mean, here we're doing it for a single n, but usually when you're doing something like this, you might make a sieve, like Sieve of Eratosthenes, which does it for all the numbers up to n. But if you only need to check for one value, then it should be simple to implement. It's harder when you have to do all the values up to n fast. We also have Euler's theorem, which says that if a and n are coprime, then a to the power of the phi of n is equal to 1 mod n. So we get the identity. And Fermat's theorem is a special case of this, where n is prime. And when n is prime, then phi of n is just n minus 1. Okay, combinatorics. That's the study of countable discrete structures. So we usually have some enumeration problem. We're given an infinite sequence of sets, a1, a2, up to an, maybe up to infinity, which contain objects satisfying a set of properties. And we want to find the number of items in each set, so just the size of the sets for a general n. Some simple cases, for example, are the factorial, so that's like the number of permutations of size n. We have the binomial coefficient. How many ways can we choose k objects from n objects? And yeah, we're ignoring order here. So some properties of the binomial coefficient. You can swap k with n minus k. The number of ways of selecting 0 and selecting n objects is just going to be 1. Take nothing or take everything. And then this property here is very interesting, and if you look at Pascal's triangle, you can see it happening. So our property was that we can subtract 1 from both n and k, and add that with where we subtract from n, but not k. So let's see, for example here, 4 and 2, subtract from both, that's this case, subtract from just n, that's this case. And if you know Pascal's triangle, the value of each item is the sum of the two that are above it, like directly above it. So this is equal to this plus this.
And along the edges, like for example, 3 and 0 or 3 and 3.
Yeah, then you just take the one value which is available to you. So you always have the identity, this identity, second one.
Mm-hmm.
You always have that along the edges here. So you always have a 1 here. And the rest are summed up from the two values above it. We could be counting how many rectangles can be formed on an m by n grid. So a rectangle needs 4 edges. 2 of them need to be vertical, 2 of them horizontal. Just like so, you get a rectangle. And the number of ways we can choose 2 vertical lines. Well, we have n of them here. 1, 2, 3, 4, 5, 6, 7 in this case. So it's just n choose 2. Same for horizontal lines. It's m choose 2. So the result is going to be n choose 2 times m choose 2, because selecting these edges is independent. We can select vertical edges and then select horizontal edges independently. This results in this expression here. And note that calculating this directly like this, so if you write down what and simplify on a piece of paper, you often get something that you can implement faster. So now you see that you don't need to implement the n choose k function here. You just have to do some multiplication.
What's the intuition here that if you're just picking 4 edges, as you go along, that the 4 edges you pick actually form a rectangle?
So if you select any 2 edges here,
Yeah.
then they will give you a boundary on the left of the rectangle and the boundary on the right of the rectangle.
Yeah, I see. Okay, yeah, sure.
And then similarly for horizontal, you get a top boundary and a bottom boundary. And because this is in a grid, these are bound to intersect somewhere. So you get the corners of the rectangle.
And this doesn't double count?
No, so because n choose k ignores order. So we just have all the ways of selecting 2 edges without considering order. And because they're independent, horizontal and vertical lines, we can just multiply them together. A more complicated case is the multinomial. We could have objects with the same value. So for example, the number of permutations on n objects, where ni is the number of objects with the ith value. The multinomial for that is denoted with this notation here. So we have n at the top, and then we have how many times each item occurs. And that is n factorial divided by n1 factorial times n2 factorial times n3 factorial, and so on. Now, number of ways to choose k objects from a set of n objects, where each value can be chosen more than once. We have n plus k minus 1, choose k. And that results in this expression here.
So it's chosen more than once. So you mean like even though you pull it out of there's an infinite number of copies in the bag, right? Like it's just because you pick one, that doesn't mean you can't pick it again.
Mm-hmm. Yep. Now, in how many ways can we divide k identical balls into n boxes? So this is the equivalent of finding the number of non-negative solutions to this equation. So the x's here represent the size or the number of balls we put into each box. And to solve this, let's imagine we have a bit string which consists only of ones, and its length is n plus k minus 1. So its length is the number of boxes plus the number of balls minus 1. Now let's select some n minus 1 bits, which we swap into 0. Then we have a string of 1s, and then a 0, and another string of 1s, and a 0. And the string of 1s could possibly be empty. And the total number of 1 will be k, because we had n plus k minus 1 1 bits, and we changed n minus 1 of them to zeros. So we're left with k. So we have k 1 bits, and each one of them represents an element. Each one of them is a ball. And these are separated into n groups. So the zeros are separating the values into groups. So the number of ways we can choose the bits to swap is n plus k minus 1, choose n minus 1, or simpler, m plus k minus 1, choose k. Another thing we can look at is lattice paths. So we start at 0, 0, and we want to get to nm. We can move up by 1 value, or move to the right by 1 value. So we start with one path to 0, 0. So there is one path to 1, 0 and 0, 1. Paths to 1, 1, we can reach there from 0, 1 or 1, 0. So we take the sum of the number of paths to those coordinates. And if you want to get to coordinates ij, it's the number of paths to get there is the sum of the number of paths to the preceding places we could have been at. So that's I minus 1, comma j, and I, comma j minus 1. Now, we could do this with dynamic programming, calculating the sum for each coordinate. But we can also consider that we have to take n plus m steps. And we essentially need to choose when do we take the up steps. So we have I plus j steps, and where do we place I of the up steps? So we have I plus j, choose I. We could have an added restriction that we're not allowed to cross the main diagonal. So, for
I'm
example,
sorry, the intuition again for the binomial coefficients, what was, I didn't quite think in.
So it's quite similar to the balls and boxes one. So consider you have a string of I plus j r's, which represent right. Like we're taking steps to the right.
Yep.
And then consider, okay, we need to swap out I of those with a u representing up. So what are the number of ways we can swap the r's with u's? And since the number of u's and the number of r's is the same, we end up in the same spot at the end.
Yeah.
So
Okay.
for example, this would be r, 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 u, 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 r, 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 u.
Yeah, makes sense.
Okay. Yep, so we could have the restriction of not crossing the main diagonal. And this, for example, is a path which does not cross the main diagonal. And the number of ways to achieve this is counted by the Catalan numbers. There are many problems which involve the Catalan numbers in some way. So, for example, number of different ways, n plus 1 factors can be completely parenthesized. We have number of stack sortable permutations of length n. Number of different triangulations for convex polygons with n plus 2 sides. Number of full binary trees with n plus 1 leaves. So these will have n internal nodes, I think. So two n plus 1 nodes in total. But it's the number of leaves which counts. And a lot more. It's I think if you go to oeis.org and input the Catalan numbers, there's a huge list of references to to papers which have been working with Catalan numbers in many different fields. And then, of course, there's another common sequence, the Fibonacci numbers. We've already gone through the definition a couple of times. And we covered how to calculate an O of n time with dynamic programming. But we can do better. So we can represent the Fibonacci sequence with matrices. And we can calculate the recurrence using these matrices. So if you have two values here, two adjacent values in the Fibonacci sequence, and you multiply this matrix with it, then you will get a vector with the next sequence, or next value in the sequence, and this value here at the top. And the idea here is we can use matrix multiplication. And we can raise the matrix to a power, so like the power of n. So if we use fast exponentiation, we can calculate this in O of log n time. So what happens here is we have our values in the recurrence here, the coefficients of the recurrence. So we have 1 times f of n plus 1, and then plus 1 times f of n is equal to f of n plus 2. Okay, and then we need to carry on the old values which we need for the next step. So we have a 1 here, and we get 1 times f of n plus 1 plus 0 times f of n. So we get an f of n plus 1 here. So we can generalize this to any linear recurrence. So here we have that the nth value is equal to some c1 times a of n minus 1 plus c2 of a of n minus 2, and so on. So we have these coefficients here. And we put those here at the top, so they get multiplied with down this all the way, and that gives us the new value here at the top. And then we want to carry on all of these values except the last one, so all the way down here. So we have this diagonal of 1s here below our coefficients. And then the last one here will have a 0. And again, we can use matrix exponentiation. So if we have a recurrence relation, which is a linear function with k preceding terms, the running time will be big O of k to the power of 3. So that's for the matrix multiplication of a matrix of size k. And then we will do log n of those. So we have big O of k to the power of 3 times log n. We'll also look a bit into game theory. So what is game theory? Game theory is the study of strategic decision making. But in competitive programming, we mostly consider just combinatorial games. So for example,
could I ask you briefly actually again about the time complexity for this linear recurrence?
yes.
The cubic term?
The cubic term comes from matrix multiplication. So the naive method of multiplying matrices is a cubic algorithm. So we want to find the value of this here item. So we have to loop through this and this at the same time. So the top row here and the column down here. And that will be O of k. And then we have to do the same for this value. Yeah, I guess here it's only k squared. No, sorry. We erase. So we're erasing this matrix here to the power of n.
Mm-hmm.
So we have k squared values here, which we have to calculate, and calculating each of them takes O of k time.
Sure.
So you take this row here and you multiply that with this column here, piece by piece, and sum those together. So that ends up being big O of k to the power of 3.
And the Fibonacci sequence is what, a special case or something?
It's more of a case where we know we have a constant size matrix. So we know the matrix of size 2. So technically this should be, k to the power of 3 where k is 2.
I see, yeah.
But it's just we know it's constant. The size of the matrix is not varying. But here we could be accepting, any recurrence, any linear recurrence.
Sure.
So if you had a fixed matrix with a larger size, but it's still constant, you would still say the time complexity is O of log n. You would just know that there's a high constant following it.
Right.
It's a slower log n than just a standard binary search over integers. Okay, so we have a pile of k matches. And the players can remove 1, 2, or 3 matches from the pile, and they alternate on moves. So the player which removes the last match will win. Now, there are only 2 players, and one of the players, which we'll call the first player, starts. Now let's assume that both players play perfectly. Who wins? And we can analyze these games with a backward intuition. So we start at the end, the finishing state of the game. We call a state n position if it is a winning state for the next player to move. And p position if it is a winning position for the previous player. So the terminal position of having 0 matches is a p position, because the player that made the move which got us to that state is the winner. Now, if every reachable state from the current one is an n position, then the current state is a p position. And if at least one p position can be reached from the current one, then the current state is an n position. So let's analyze this. We have a p position here at our terminal state. The positions which are reachable from the terminal positions are n positions. Now, position 4 can only reach n positions. So you look from 4, you can reach 3, 2, and 1. The next 3 positions, they can all reach a p position. So here we can go to 2, we can go to 3, and we can go to 4. Knowing that 4 is a p position, we would always choose to go there. Because then we know that the next player can only make moves which get them to an n position. And then we can fill in the rest in the same manner. So here we can see a clear pattern of n and p positions. If you look at this, where do p's occur? What properties do the integers have to fulfill so that we have a p? Get one at 0, get one at 4, and 8, and 12, and 16, and 20. So these
And
are
they're
just...
always 0, when you mod.
What did you say? 0 when you mod?
Mod by 4.
Yeah, 0 when you mod by 4. So these are multiples of 4. And it's quite easy to prove it. This was even an exercise in old course at Reykjavik University for the first semester, which is no longer taught. And there are many games which can be analyzed in this way, and they don't have to be one-dimensional like this. So what if we had n piles instead of 1? What if we can remove 1, 3, or 4 matches instead of 1, 2, and 3? So let's look at a game called Nim, and this game is kind of the most fundamental combinatorial game. So we have n piles, and each of them contain some number of matches. Let's say xi for the ith pile. Now, a player can remove from exactly one pile, but they can remove as much as they want. And the player who removes the last match wins. Again, there are just 2 players, and we have a first player which starts, and they alternate on moves. So let's assume both players play perfectly. Who wins? And we could analyze this game with the n and p position, but it's not trivial to generalize it over all the piles. But someone already did that for us. So Bouton's theorem states that a position in Nim is a p position if and only if the XOR, so the exclusive OR, bitwise, over the number of chips is 0. And this theorem extends to other sums of combinatorial games. What you can do, if you have a combinatorial game, you can find a way to map that game to Nim.
And I guess by chips you mean matches?
Yeah, sorry, matches. I mean, this is usually just done with stones. Like Nim is described with stones, piles of stones. But yeah, it's supposed to be matches. Yeah, so what you can do is you can map your game to Nim. There's also a principle known as the max principle, minimum excluded value. There's a thing called the Sprague-Grundy theorem. These are all very useful in combinatorial games. And if you map your game to Nim, then it's often easier to solve from that point, because we know the solution to Nim. It's just using the XOR. Another thing to keep in mind is when doing combinatorial games is that you have these states in the game, and then you can transition to different states by making a move. This sounds a lot like when we're doing dynamic programming. We have states and transitions. So you can actually use dynamic programming to solve a combinatorial game. Okay, that's it for the lecture. Yeah, I was gonna put the problems in on Catis. Let's see. Okay, so the problems we have are jumbled compass, so that's compass, we have which base, triangle, strange ID for something called Sierpinski's circumference. We have the meow factor, number 1, I think, yeah, number 1. We have the snapper chain, and then 2 bonus problems, immortal porpoises and the A plus B problem. So this is porpoises and A plus B. You need 3 points to get a full score, and they're all 1 point. Or each one of them is 1 point. So you need to solve 3 problems. Are there any questions at the end? Actually, I have a question. So the plan tomorrow was to not have a lecture. However, geometry is a topic I really like, so I was wondering if you would want me to go over the slides instead. So instead of just, being around to assist from before noon, I would record the lecture and cover the content, even though it's not on the final exam. Does that sound good to everyone? No objections?
There's no objection from me. So I can also just look at it at YouTube.
Yeah,
Okay,
yeah,
yes.
yeah. I would record it,
Okay, yeah. Fine.
and then I'll record strings as well for during the weekend, just solo.
Okay, yeah.
Okay, so I'll have a lecture tomorrow on geometry. If you get into competitive programming, you're probably gonna hate geometry because of precision errors. But the problems are often very nice. It's just hard to implement them. Alright, good luck with the problems, and see you later.